So tonight, you submit the second mission, and yeah. So now this upcoming week, we're going to be going over probability tables and relative risk. So we can take a look at that lecture. So here's where we are in the course map. So we've completed now these first three modules on introduction to data, categorical data, and numerical data. And this upcoming week, we're going to be going over probability tables and relative risk. So we can talk about probabilities as proportions. And the idea is that we have a probability of an event occurring, and we can determine whether it's more or likely to occur. So in this week, we're going to use the case study that we're going to be a sociologist, and we're looking at if there's any association between people's income and whether they have health insurance, so whether they're considered to be poor or not poor, and whether or not they have health insurance. So here's what the data set looks like. We see we have all these categorical variables. We have some numerical variables like age, income, hours per week, etc. But sex and married and race and whatnot are all categorical. We can see here there's the health insurance variable, so it's either yes or no for whether or not they have health insurance. And we can create a simple table of proportions for the variable health insurance. This is using R. This is data output using R. So here we can see there's 343 total subjects in this data set. Of those, 303 of them have health insurance and 40 of them do not have health insurance. So what we can do is just represent this 343, the total number of subjects, as 1. And then what we can do is divide both 303 divided by 343 to get 0.88 or 88%. And 40 divided by 343 will be 0.12 or 12%. And we can check that if we add these two numbers up, they'll equal the whole of 1. So this is a way of representing probabilities as proportions because we can say that 88% of the people in the study have health insurance and 12% do not. So you can say if you're randomly choosing someone from this study, there's an 88% chance that they have health insurance. So probability can be counterintuitive, and it can be a tricky subject for students if they've not seen it before. So don't get frustrated if probability seems a bit tricky or counterintuitive, because that's just a fact of what probability is. And actually, the casinos take advantage of that. There's an example of if you've ever been to a casino, they have the roulette wheel, and now in the new casinos, they'll have a board above the casino, above the roulette wheel. They'll show you the previous roll. So if it landed on a black number or a red number, and it'll show you, so that the idea is if you're walking along the casino and you see that screen and you see that the last 10 times that the ball rolled, it got a black, you might think that it's due for a red roll to come out the next turn, but it actually doesn't work that way, because each individual roll of the roulette wheel is an independent event. Past events don't affect future events in this case. So that screen there is deliberately designed to mislead you into thinking that somehow the past outcomes will affect future outcomes. And that's that's a counterintuitive notion because that's actually false. So just understand that, within this concept of probability, that things can be tricky or not be exactly as they seem. So some examples of probabilities are a simple coin toss, the probability of getting a heads, having health insurance or not, which is what we're looking at, or it could be something like working more than 40 hours a week, will it lead to depression or not? So probability deals with random phenomena. So this is that the phenomena, so that the event is uncertain of the outcome. If we knew the certainty of the outcomes, we wouldn't have to deal with probability. So this is something that we're dealing with some degree of randomness. And the outcomes have to be exhaustive and mutually exclusive. And that means that we have to be able to know all the different outcomes of our event, and they cannot be, so that they're mutually exclusive, meaning that they both cannot occur at the same time. So that, to give you an example, when you flip a coin, that coin can land on either heads or it could land on tails. It can't land on both heads and tails at the same time. That would violate the principle of mutual exclusivity. And those are exhaustive events because we only have two outcomes. It could only be heads or it could be tails. It can't be something other, something else that we have not accounted for. That's the definition of exhaustive. So, like we said, exhaustive is listing all the possible results. We have to know what those are, and mutually exclusive is that you cannot have two of those events occurring at the same time. And so we can use this notation to describe our sample space with S is equal to the different outcomes listed out and up to K possible outcomes. It can be infinite, but we're not going to discuss events that have infinite sample size. So here with a weight gain example, you can have the sample size equal to whether you gain weight or do not lose weight, or gain weight rather. And then we could also specify it as gaining weight, losing weight, or no change in weight, or etc. You can make it as complicated as you want. However, weight gain and weight loss are mutually exclusive because at the same time, you can't both be gaining and losing weight at the same time. But no change in weight, losing weight, and gaining up to 50 pounds and gaining more than 10 pounds are collectively exhaustive, but not mutually exclusive. As you see here, if you're gaining more than 10 pounds, you could also be gaining up to 50 pounds. So that's going to violate the principle of mutual exclusivity. So here, this is an example where we have mutually exclusive and collectively exhaustive outcomes, the either gaining weight or not gaining weight, because these are two distinct and separate outcomes. So now we can assign probability values to each of these events. And to do that, we use a notation here. So we typically abbreviate our event and we can call it A. And then we can find the probability of A occurring, which we can shorten as PR of A or P of A. It's the same, means the same thing. These are just shorthand abbreviations for describing this probability. Now, when we assign a probability value to this event, it will be a number that's between 0 and 1 inclusive, meaning that it can be a number between 0 and 1, but it's also can be 0 or 1. So the way we understand this is the 1 is a 100% likelihood of the event occurring. A 0 will be a 0% chance that the event will occur. And then you could have any number in between those that will represent the probability. So you could have 0.5, which will be the 50% chance of the event occurring. So like a coin toss is an example of 50% probability event. If you flip a coin, it's a 50-50 chance that you'll get heads or tails. And we can calculate that using this formula. So the probability of an event occurring is, in the numerator, the number of trials in which the event did occur, or the number of successes, divided by the total number of trials. So here, like we said, we can have any number between 0 or 1, including the 0 and 1, and we could have any number between those two numbers. So we could also talk about odds as well, which is the ratio of the number of outcomes in which an event occurs versus the number of outcomes in which an event does not occur. So if you hear that, if you see this notation that the odds of a fair coin landing heads up is 1 to 1, it's the same thing as saying there's a 50% probability of it landing. So just be mindful of this notation. You can say that the probability is 1/2, or you could say that there's a 1 to 1 chance. Those are the odds. So make sure that the probability is inclusive from 0 to 1. It cannot be above 1, and it cannot be below 0. If you ever get an answer like that, it means you've made a mistake, because the definition of probability is it's going to be a number between 0 and 1 inclusive. And the second rule of probability is that the probability of a set of all outcomes must be 1. So you have to be able to add up all those exhaustive events and sum it equal to 1. The sum cannot be any number other than 1. If it's less than 1, then we're missing a possible outcome. We didn't account for that. If it's greater than 1, then 2 outcomes are happening at once, which is going to violate that principle of mutual exclusivity. And the third rule of probability is the complement rule. So the complement rule says that when we have the probability of not A, and this notation means not A because of the little line that's above the capital A letter here. So we interpret this as not A. And the probability of not A is equal to 1 minus the probability of A, because these are exhaustive, mutually exclusive events. So you either have A occurring or A not occurring, right? And those sum up to 1. So if we want to know the probability of not A occurring, all we have to do is 1 minus the probability of A, and this will give us the probability of not A. So there's 2 ways to represent the probability of not A. You could either have that line up top, or you can denote it by A with this little comma mark here. So so and it's also known as the complement. So if you're hearing about the complement, just know it represents 1 minus it's 1 minus that event, or not that the probability of that event not occurring. So this is kind of a little bit of a joke, and saying that, as you can see here, there's a Venn diagram, those who can read Venn diagrams and those who can't. And this shows that they're mutually exclusive because you can't have an overlap between those. If you had an overlap here, that would violate the rule of mutual exclusivity. So there's 3 basic rules of looking at a Venn diagram. So we can see here that the probability of the sample space will equal 1. Here we have the probability of A, represented by this blue circle, and that could be any number between 0 and 1 inclusive. And the probability of not A will be 1 minus the probability of A, which will be outside that blue circle. So for health insurance, going back to our case study, we found that 88% of the people have health insurance and 12% do not have health insurance. And just to reiterate, if we add those 2 up, that equals 1. So that's good. That fulfills all our rules of probability. And we see here that they're both mutually exclusive and collectively exhaustive outcomes, because you can't both have health insurance and not have health insurance at the same time. You fall into one of those 2 camps. And those are the only 2 options in this category. We don't consider other options besides having health insurance and not having health insurance. Thus, we can represent the sample space as this notation. S is equal to no, not having health insurance, or yes, having health insurance. So if we call the probability of having health insurance the probability of I, then the probability of I is equal to 0.88. If we call the probability of not having health insurance the probability of not I, then you can just do the complement of 1 minus 0.88, which is equal to 0.12 or 12%. Both of these values lie between 0 and 1 inclusive, so those fulfill the probability laws. And you can see here that 12% is less likely to occur, and 0.88 would be somewhere over here, more likely to occur. So our conclusion is that Americans are more likely than not to have health insurance if we look at the probabilities, because we said that 88% have health insurance and 12% do not. But be careful with the probabilities. So this is just a funny example because there was this statistician in England, he was born in Seattle, but he was in the UK, and he tried to calculate the probability of him finding a girlfriend, which he found to be very, very, very small, much smaller than 1%. As you can see here, he calculated. He said it was more likely that we'd find aliens than for him to find a girlfriend. And little did he know, he actually ended up finding love and getting married. So it turns out that despite his calculated probabilities of 1 in 285,000, he actually was able to find someone. So probabilities, there are different ways. There's 3 main ways of obtaining probabilities. The first is the empirical or the experimental method. The second will be the logical method, and the last one is the subjective or personal method. So the empirical approach can be solved empirically from our formulas. So in this example, as we said, we can define the probability of any event occurring as the number of trials in which the event did occur, divided by the total number of trials. So this method has some limits. It is the most common way to assign probability values, but it may be misleading if you base the probabilities on a small set of trials. So whenever you're dealing with probabilities, the larger your sample size is, the closer you get to find out the true probability of an event occurring. If you have a small sample size, like if you flipped a coin 3 times, it's very possible for you to get heads 3 times, and you conclude from that that the probability of getting a heads is 100%. But we know that's not true. The probability of getting a heads is 50%. And the reason why you're getting 100%, you're getting a false probability, is because you have a small amount of your sample size. You're only flipping it 3 times. If you flip the coin 1,000 times or 10,000 times, you're more and more and more likely to get a 50-50 split between heads and tails. And that will get you to your true probability of something occurring. So this is an important concept, not just for probability, but also for study design. And when you're looking at studies, you should always consider what their sample size is, and do they have enough power in their study for them to justify their results. There's also the logical approach. So the logical approach is the probability of an event occurring is equal to the number of outcomes in which the event occurs divided by the total number of possible outcomes. And it requires that each of the possible outcomes are equally as likely. So we can use this for casino games, rolling a dice. Yeah, there's 6 sides to a fair dice, so the probability of rolling any given side is 1/6. Flipping a coin, we have 1/2. There's 50-50 chance of landing on heads or tails. So the limitations of this is it's really for straightforward basic games and fair gambling. And most random phenomenon do not fit in this line of logical approach. So it's unfortunately only you're only able to use it in limited situations. And for a subjective or anecdotal method, this is really just based on one's belief or judgment. And if you ask me, this is the worst way of calculating probabilities because they can be based on some evidence, all of the evidence, or no evidence whatsoever. And it can be wildly off base if someone's uninformed. So, someone saying, oh, I know someone who smoked until the age of 95 and never got lung cancer. You don't want to base your probabilities off anecdotes or stories. You want to be able to base them in evidence and empirical formulas. So probabilities are the way of saying how likely or unlikely an event is occurring. And they may be obtained in those three methods that we discussed, empirically, logically, or subjectively. And we obtain them from real world data. And the rules of probability are going to work no matter how we obtain our probability values. You're always going to have those basic rules of probability holding, like that we discussed earlier. So now we can talk about probability tables, and this is a nice way of organizing your probability data, and it really comes in handy once the probability gets a little bit more complicated, because you'll have subgrouping and you'll have conditional probabilities. This is a good way to organize everything and really make it so that you're not confused. So let's go back and take a look at the case study, the American Community Survey. And our research question is, overall, how likely are Americans to be uninsured and economically impoverished? So we're looking for those that are the most at risk. They both have no health insurance, and they also are poor from the poverty line standpoint. So we can look at our data set here again, and we can form a probability table, which is a table of unconditional proportions. And when we're conducting research with categorical data, you'll have questions like the one that we just asked. So questions involving two categorical variables. And to fully answer these questions, it's very helpful to know how to work with the probability table. So we're looking at two random phenomena, an event A or B, and the probability of A and B both occurring, we can use this notation of probability A and B. Two events are joint or mutually inclusive if the occurrence of one event is compatible with the occurrence of the other, and they can both happen at once. Conversely, two events are disjoint or mutually exclusive if the occurrence of one is incompatible with the other. So if they can't happen at once. If the events are disjoint, then the probability of A and B will be equal to 0. So disjoint or mutually exclusive events cannot happen at the same time. You can't flip a coin and get both heads and tails. But joint probabilities, mutually inclusive events, can happen at the same time. So to give you an example, well, here we can say flipping a coin and drawing an ace from a deck of cards, or the example that we're looking at, which is being both impoverished and not having health insurance. And this is how they're represented as a Venn diagram. So here we can see there's joint probabilities because we see that there's an overlap here shaded in the green region. This is representing the probability of both A and B occurring at the same time, as you can see. And here we have disjoint probabilities. These are disjoint because there's no overlap, as you see here. The blue and yellow circles there's no overlap between them at all. There's no shaded green region. So that means that these are disjoint probabilities. And the example that's used here is the joint example is being born into a wealthy family and working in an investment bank. So that can obviously both happen at the same time. In the disjoint example, you're looking at probability of being born into a wealthy family or the probability of being into a poor family. You can't be born into both at the same time. So that's why they're disjoint probabilities. So when we're working with joint probabilities, we can assign the different probabilities to each of the different regions as shaded here. So we see here the probability of A is this blue shaded region, which is represented by the probability of A and B, the green region, and the probability of A and not B, which is this blue region. So if we add these two up, we'll get the entire probability of A. And we can look at this with the Venn diagram here to show that A here so the probability of A here is 0.35, which is 0.2 plus 0.15. Can you guys still hear me? I just want to make sure that the volume is still working. Okay, great. So here we're looking at the health insurance data, and we're trying to look at whether the probability of being both impoverished and uninsured. So here we have a contingency table, and we said that the sample size is 343 respondents. So here we're having our probability table. This is a unconditional probability table. Up top, we have those who have health insurance, and we see here that 303 people have health insurance, and 40 people do not have health insurance. So that adds up to our grand total of 343 people. And then on the left side, they're categorized to being either poor or not poor. And we see here that there's 130 poor people of the 343, and there are 213 non-poor people. So this is how our 2x2 contingency table will look like. And sometimes it's easier when we draw in these lines. We can look at the margin totals here. This is the grand total. So events that are listed horizontally and vertically are mutually exclusive and collectively exhausted, which is a requirement for converting to a probability table. And by dividing each of these numbers by the grand total, 343, we can convert this contingency table into a probability table to represent each of these different groups as a probability of the whole. So here we can see that there, like we said earlier, there's 88% who have health insurance and 12% who do not. And here we can see that there's 62%, 0.62 out of 1, are non-poor, and 0.38 of the people in this group are poor, or 38% of them. And this is a table of unconditional probabilities. So here is what it would look like. You can just, within R, instead of making unconditional proportions and then having to, without having to make the contingency table and dividing to get the proportion table, you could just, in R, use a command to make a proportion table straight away. So this is how it looks like in R, your outcomes. So these are your marginal probabilities, like we spoke about. This is the probability of having health insurance. If we add them up, these two, we get 1, which is important. So if you add it both horizontally and vertically, you're going to get 1. And you just want to double check that and make sure of it, because that's a law of probability. And if we look inside the table, these are what's called your joint probabilities, and they refer to the two events occurring at the same time. So in this case, the probability of not being poor and having health insurance is 0.59, or 59% of the people are not poor and have health insurance. And if we add all of these joint probabilities together, we're also going to get 1, which is the sum of the spaces. So if you add up the marginal totals across, you're going to get 1, and if you add up all of these joint probabilities within the box, you're also going to get 1.
So the research question that we were asking is, how likely are Americans to be both uninsured and economically impoverished? So here we could just look at those who are poor and those who do not have health insurance and find the corresponding value here, which we see is 0.09 or 9%. So we can say the probability of living in poverty and having no health insurance is 9%. So it's fairly low, right? But say if we were to look at those who have no health insurance and are living in poverty, that would be extreme vulnerability. But you can describe overall vulnerability as either having no health insurance, living in poverty, or living in poverty and having no health insurance. So those are different examples. If you have that last example where you have an or probability, that requires the use of the addition rule. And the addition rule is something that you'll use when you have two events and you want to know the probability of at least one of those events occurring. So to use the addition rule, we say that the probability of A or B is equal to the probability of A plus the probability of B minus the probability of A and B occurring at the same time. And we need to use the addition rule because it avoids double counting that joint probability. Just some recap on notation is when we use probability of A or B, we could substitute the word or for this U, which would represent the union of the two sets. And the probability of A and B is sometimes written as P of A and then that same U but upside down B, which will represent the intersection of those two sets. And we can view the addition rule as a Venn diagram here. So the probability of A or B is the probability of A plus B minus the probability of A and B, which is this green overlap region. Here you have a disjoint probability. So you don't have any region where there's a probability of A and B. So since that is equal to 0, your probability of A or B is simply the probability of A plus the probability of B because you have no overlap. And here is just describing that in more detail and explaining the concept that we don't want to double count that joint probability. That's the real reason for the addition rule. So here we show the probability of A or B is the probability of A, this entire blue circle shaded in blue, plus the probability of the yellow circle, subtracting by this green region, which is the probability of A and B. So here, if we want to know what the probability is of living in poverty or having no health insurance, the way we could calculate that is we're looking at those who are poor, which is 0.38, and we're looking at those who have no health insurance, which is 0.12. And those who have no health insurance and are living in poverty is 0.09. So in order to calculate the probability of being poor or not having health insurance, we're going to use the addition rule, 0.38, the probability of being poor, plus 0.12, the probability of not having health insurance, minus the overlap, which is at 0.09, and we get our final answer of 0.41 or 41%. And then so from that result that we know that there's 41% of these people have some kind of vulnerability, being that they're either poor or they don't have health insurance. You can conclude that there's a fairly high probability that Americans are socioeconomically vulnerable. While we said that the extreme vulnerability group of not having health insurance and being poor is only 0.09%. If we look at being either poor or not having health insurance, that's representative of a lot more of the group at 41%. So, the important things to know are contingency tables can be converted to probability tables. The cells of a probability table give joint probabilities, while the margins give marginal probabilities. And we can use the addition rule to help us answer questions about at least one event occurring. And then finally, we're on part 3 of the lecture. This is the last part. So we'll discuss relative risk and conditional probability. So relative risk is a commonly used measure of association. It uses conditioning of some exposure. And it's frequently used in biostatistics and the medical literature because it usually looks at an exposure and a subsequent disease. So we can look at, let's say, smoking and lung cancer. So if we said that the relative risk of smoking on lung cancer is 5, that means that smokers are 5 times more likely to develop lung cancer than non-smokers are. So that's colloquially what a relative risk is. That's how we understand it. And we're going to go over how to calculate it. But in order to calculate it, we have to first discuss the concept of conditional probabilities and the difference between conditional and unconditional probabilities. So when we talk about just the regular probability of A, that's going to be an unconditional probability, which in our probability tables are also called the marginal probabilities. And it tells us the probability that event A occurs. So here, these are the marginal probabilities shaded in blue, also known as the unconditional probabilities. The conditional probabilities are different. These are asking, given that we know B has happened, what is the chance that A happens? So we can say, if you're overweight, what is the chance that you'll have diabetes? Or if a child grows up in a poor neighborhood, what's the chance of them developing a mental health issue, problem? So this is good to know that if you ever hear the word if or given in a problem, just know that you're more likely to be using conditional probability. Those are signal words that you're going to be using conditional probability. So this is conditional probability. We can use that for, let's say, breast cancer. And this is talking about a screening test, but just to give you an example, you might say that the probability of developing breast cancer amongst Americans, let's say, might be 10%, or just say it's 10% for argument's sake. But that's for all the Americans. If you subgroup them to men and women, you could say, given that you're working with a man, what is the probability that he will develop breast cancer in his life? That might be much lower. So that might be 2%. And then you might look at given that if you have a woman, what's the probability that she develops breast cancer? That might be much higher. That might be 15%, for instance. So this is the idea of conditional probability, and we can see how when we condition, we can have different results than from the unconditional probability. So it's important to be mindful and understand this concept and this phenomenon. So this is how we denote conditional probability. We express it as the probability of A, and then this solid vertical line means given, and this is the conditioning event, B. So we read this as a probability of A given B occurs. So we use conditional probabilities to help us find out if two events are related and whether they are independent or dependent. If the two events A and B are independent, then the probability of A given B is equal to the probability of A, or the probability of B given A is the probability of B. If they are not independent, then they're going to be dependent. So frequently, you're going to be working on variables that are dependent, because there's the effect of one will affect the other. Independence is essentially equivalent to saying that learning that one event occurs does not give us any information about whether the other event occurred. When events are independent, it's very likely to find joint probabilities. So that's easy. You could just multiply the two unconditional probabilities. So if you know that A and B are independent, then the probability of A and B is just simply the probability of A times the probability of B. But this is a very strong assumption because events are rarely independent in reality, and we usually are not able to simply just multiply them. But if you are working with independent events, you can do this. So we have the multiplication rule for the use of finding these joint probabilities for dependent events. And we could say that the probability of A and B is equal to the probability of A given B times the probability of B. Or similarly, that the probability of A and B is equal to the probability of B given A times the probability of A. So this multiplication rule can help us when we have conditional and unconditional probabilities when we want to calculate the joint probability. And we said that if they're independent, then the probability of A given B is just simply probability of A, so that it simplifies into the formula that we saw before, so that the independent events are easier to calculate. The conditional probabilities we can calculate using this formula, that the probability of A given B is equal to the probability of A and B divided by the probability of B. Or similarly, if we reverse this, the probability of B given A will be the probability of A and B divided by the probability of A. So these are two different concepts, so be mindful of that as well. The probability of A given B is not the same as the probability of B given A. Those are two separate and distinct probabilities. So just be mindful of that and don't get confused on that. So if we have independent events, then the probability of A and B is just simply the probability of A times B. So we can find the probability of A given B is just equal to probability of A times B divided by probability of B. And like we said, as a general rule, the probability of A given B does not equal the probability of B given A. So just be mindful of that. And what you're conditioning on does matter. So they might sound like they're the same thing that you're looking at, but they're not. So working with conditional probabilities, Venn diagrams are not that helpful for this. The two ways that we're going to teach you to approach this is we can use probability tree diagrams, which are one useful way of keeping track of your conditional probabilities, and also the probability tables, which we've already gone over. Those are two great ways to visualize your conditional probabilities, so that it's not as confusing. So we could use probability trees, and this is what a probability tree looks like. We have the probability tree for a single coin flip. It can be either heads or tails, and we put the probability of each of those two events occurring as 0.5 for each of those two legs of the probability tree. So if we add these two up, we get 1, which is the total sample space. Now we can flip the coin twice. So this represents the one coin toss. You have either heads or tails. And then you're going to then flip that coin again a second time. So you could either get a heads on the first round, and you get a heads on the second coin toss, or you get a head on the first toss and tails on the second, and then, you know, so there's all these different possibilities. Now, if you wanted to calculate the probability of getting a heads twice in a row, so flipping the coin once and getting a heads, and then flipping it another time and also getting heads, we can multiply across the two branches of the probability tree to find the probability of that outcome. So here we have 0.5 for the first coin toss and 0.5 for the second toss. So if we want to know what the probability of getting heads twice in a row, it's 0.5 times 0.5, which is equal to 0.25. So you have a 25% chance of that occurring. And you can see that because there's 4 outcomes. So that's 1 of 4. So each of these will have a 25 percentile chance of occurring. And if you multiply them all across, you're going to get 25 for all of them. And you add them going from top to bottom, that's going to equal to 1, your total sample size, which is space, which is good. And just the structure, we could say this is the probability of B, this is the complement probability of not B. And we can also use conditional probability here. So we could have the probability of B or the probability of not B. And then from there, we can say the probability of A given B, because the conditioning statement B is what's given. So here we're saying B did occur, and what is now the probability of A now occurring given that B occurred? So in order to calculate that, we multiply the two probabilities of the tree occurring and get a given probability. Likewise, we can calculate the probability of not A occurring given not B occurring. So that would be looking at it here, probability of not A after given probability of not B. So this is a nice way to keep track of your different conditional probabilities so it doesn't become too confusing. And then you can simply use the multiplication rule to multiply across, and if you ever need to, you can add going from top to bottom to get your total sample space, or if you just want to add these two, you can do that and find the probability of that. So here we can see that if we're trying to calculate what the probability of each of these, we can just multiply across and find those probabilities using the multiplication rule. And here we're going back to our example with the health insurance example using the ACS data. And we're asking, given that a person is poor, what is the probability of having no health insurance? So we can denote that as probability of having insurance given they are poor. And the way we can do that is we are looking at the probability of being poor and insured divided by the probability of being poor, right? So here we see that the probability of being poor and insured is 0.29, 29%. And the probability of being poor, the total probability of being poor, is 0.38. So this is your conditioning statement. Probability of being poor. So this is going to be in your denominator, 0.38, and the numerator is going to be the joint probability, 0.29. So we can also use a probability tree. So in this case, we're looking at the probability of being insured given that you're poor. So since it's conditioning on being poor, on the first probability tree, we're going to go with the probability of being poor, 0.38. We're going to go up here. And then we're looking at, given that you're poor, the probability of being insured. So it's this option, this conclusion, and we can calculate it by taking the probability of being poor, this 0.38, and we can multiply it across and we can get 0.29 as the probability of P and I. So given the respondent has health insurance, what is the probability of being poor? So we can use our conditional probability here. So probability of being poor given that you have insurance. So this is not the same thing as what we looked at in the previous example. This is the reverse as far as the conditioning statements here go. So we're going to look at the probability of being poor and insured, which again is 29%, 0.29. And now we're going to be dividing on whether they have insurance or not. So that's the conditioning statement, and that's 0.88. And we can see that there's a 33% probability of them being poor given that they have insurance. So that's it's a much less likely event of occurring than the previous example, which was given the respondent is poor was the probability of having insurance, which was 0.76. So as we see here, what you're conditioning on does matter. So we said those last two probabilities, they were not the same thing. And the only thing that we changed was the order of the conditioning statements. And you see here, we got big difference in the two answers here. So the question is having health insurance independent of being poor? And how do you know? And the answer is no, because if they were independent, then we can just multiply the two and find what the joint probability was. So in this example, 0.29, the probability of being poor and insured, does not equal the probability of 0.09 plus 0.29 multiplied by 0.59 plus 0.29. So if you had independent events, that they would be equal, those two. But since you did not get the same answer using those two ways, we know that these events are dependent on one another. So, and that makes sense intuitively, because having health insurance, certainly is dependent on whether you are poor or not. There is some one of these things does affect the other. And then getting back to the relative risk concept, it's called the relative risk. It's the ratio of the probability of an event occurring in an exposed group, and it's comparing that with probability of the event occurring in a non-exposed group. So we said it's used quite often in biostatistics and medicine. So you can consider smoking to be an exposure, but we could also relate it in psychology and sociology. For example, poverty could be an exposure. So in this example, we could use the poverty being poor to represent an exposure, and the outcome would be whether they have insurance or not. And this is the relative risk formula. You're looking at the probability of an event occurring given that you were exposed in the numerator. And in the denominator, you have the probability of the event given that you were not exposed. And to interpret relative risk, if you have a relative risk of 1, that means there's no difference in risk between the two groups and that there's no association. A relative risk of greater than 1 means that the event is more likely to occur in the exposed group than the unexposed group. And if it's less than 1, it means that it's less likely to occur in the exposed than the unexposed. And we said that the understanding of a relative risk is if you have a relative risk of 4, the exposed group will be 4 times as likely of having that outcome occur to them than the unexposed group. Or a relative risk of 0.5 means that they're half as likely to have the event occur to them than the unexposed group. So here we can calculate what the relative risk of having no health insurance is based on living in poverty. So we just have to calculate the probability of not being insured given that you're poor, and we're dividing that by the not exposed group. which is the probability of being insured given, probability of not being insured given that you're not poor. So the exposure here would be whether you're poor, and we're looking at if that has an effect on you not having health insurance. So we can calculate the numerator to be 0.24 using this conditional probability, and the denominator to be 0.05. So when we put it in the relative risk formula, we get an answer of 4.8 times. So we can interpret this by saying the respondents who are poor have 4 times the risk of being uninsured than those who are not poor. And we can also calculate that. This is just showing how the calculations were calculated from the contingency table as well. So there are limitations to the relative risk. It's telling you that there's an association between the exposure and the outcome, but it doesn't prove any causality. In statistics, we don't prove causation, but we can say that there's a correlation or that there's an association between these two. And these are also relative risks. So you're not calculating the actual risk, but they're relative to those who are unexposed. So for an example, you could say that having a CT scan as a child will make you 3 times more likely to have bone cancer as a child, but the actual risk of getting bone cancer as a child is very small. It's 1 in 10,000. So even having a CT scan, while it may increase it threefold, it's still a very, very unlikely event. So you shouldn't, if a child needed a CT scan, we wouldn't not give it to them for fear of bone cancer development, because while the relative risk is higher, the actual risk is still very small. So the takeaways here are that conditional probabilities are usually based on a subset of data. If we have independent events, we could just multiply them together. And we have the relative risk, which is the ratio of the probability of an event occurring in an exposed group to the probability of the event occurring in a non-exposed group. And it's expressed as terms of times the risk. So 5 times the risk. And that was the probability lecture. So that's the lecture that you're going to be going over this week, and that will be tested on this upcoming problem set, this upcoming mission for you guys. Does anyone have any questions? So I'm happy to answer any questions if anyone has any questions on the lecture or any other questions. There's not too much R calculations, R codes for this material. Basically, you're taught how to make the probability tables and how to interpret that. But as far as having R calculate probabilities for given events, that you're probably going to have to do that on your own. So you're going to have to take the probabilities from the chart and be able to interpret them. So especially with the conditional probabilities and such, it's good to be able to recognize within the probability charts which ones are your conditional probabilities and which ones are the unconditional probabilities. Those are the margin totals and the difference between the two. So I'd say, you know, and if this topic does seem tricky, don't be discouraged. Probability can be difficult for students who haven't been exposed to it before. So I'd say, you know, definitely, you know, the more practice with this material, the easier it gets. Yeah, I'd say familiarizing yourself with the formulas is a good idea. Being able to understand the concept of conditional probabilities and how to calculate them, and how the relative risk formula works, and why it works that way. I'd say if you can understand the difference between these things, conditional probabilities and unconditional probabilities, and that makes sense to you, and the formulas all make sense to you, then it'll be a lot easier to go through this material to realize why these formulas are set up this way, and how that comes to be. It becomes a lot easier to approach them. So this week you'll be going over the probability and relative risk, and then there'll be 3 more modules: the correlation analysis, simple linear regression, and basics of sampling. And then you're going to have spring break. And then once spring break is over, you're going to have your first exam, which will test the material covered in the first half of the semester. And then from there, you have the second half of the semester, and then the course will finish up. So So the question is there a time when you have a problem that will have you use both unconditional probability and a conditional probability? And the answer is yes. I mean, you're going to have to use that for the multiplication rule. So I mean, this is a conditional probability here. So, you know, with the relative risk, you're comparing 2 conditional probabilities, but if you're going to be calculating a conditional probability in itself, you're going to be using unconditional probability, right? Because the definition of a conditional probability here, so So here, so even just calculating what your conditional probability is, you're going to use unconditional probability. So, you know, if you're asked to calculate a conditional probability, you might have to use unconditional probabilities. And then if you were asked to find the relative risk, you might have to use a conditional probability in that calculation. So if I asked you to find the relative risk from a probability table, you might have to first calculate the two conditional probabilities that you need, which remember in the numerator, you're looking at the probability of an outcome occurring given that you're exposed, and the denominator would be the probability of that outcome occurring given that you're not exposed. So those are two conditional probabilities, but in order to find those conditional probabilities, you're going to have to find the joint probability of the event given the exposure divided by the conditioning event, which is your exposure here. So, you know, that's an example of using both conditional and unconditional probabilities, because here you're dealing with unconditional probabilities to calculate a conditional probability, and then when you're dealing with relative risk, you're going to deal with the two conditional probabilities for the two groups to come up with your final answer of your conditional probability of your relative risk, rather. Any other questions? Okay, great. Well, if there's no other questions, good luck this week. We'll have more sections next week again, meeting up again Monday through Thursday. Can we have questions from the last module? How do you mean, Fatima? Yes, you want to ask a question from a previous module? Yes, of course you can ask that. Okay. Do you have a page number? (116). Okay. Is it this question, or should I keep going down? So is this the questions that you had on these calculations? So this is showing you how to understand variance, and here there's 5 different points in this set. So here you have point at 6. Here you have a point at 1. Here is a point at 0. Here's a point at -1, and here's a point at -3. And these are all on the number line, as you can see here. And the way to calculate your variance is you're going to add up all of the, so it's the sum of the squared differences. right? And the reason why they're squared is because we want them to be positive numbers, because we can't deal with negative numbers and to calculate the variance. So we square them in order to make everything positive. So in order to calculate the variance in this example, this was 6, right? This is the point's at 0.6, positive 6. So we take 6 and we square it. So 6 times 6 is 36. So that's what it's showing you here. This is at 0.1. So in order to calculate the difference for this, the squared difference is 1 squared. 1 times 1 is 1. This point is at 0. It's at the 0 point on the number line. So 0 squared is going to be 0. So that's just simply 0. This point's at -1. So we can take -1 multiplied by -1. That will give us positive 1. And this is the point at -3. So we could do -3 squared, which is -3 times -3. That'll give us positive 9. And then once we have all these numbers, we can sum them all up and get 47. So 9 plus 1 plus 0 plus 1 plus 36. It was just going from bottom to top. 9, 1, 0, 1, 36 is equal to 47. And because there's 5 of those points, we can average it. So we can take 47 divided by 5 to get the variance here. Does that make sense? So here we could look at this example. So we have 5 points here. So we have a point at +2, point at +1, a point at 0, a point at -1, and a point at -2. So we're going to square everything here. We're going to add them all up. We get 10. And there's 5 points. So we do 10 divided by 5, and we get 2. So we're just calculating our variance to equal 2 here. That makes sense. And this is just an explanation on how we're calculating variance, just to illustrate the concept behind the formula. Here's another example where you have 2 points at +1 and 2 points at -1 and 1 point at the 0 line. So if we square everything, we add them all up, we get 4. And then we divide by 5, which is the number of points here, and then we get 0.8. So this is a smaller variance, as you can see, than in this previous example. And that makes sense because these are closer to the mean, to the central point. So we expect the variance to be smaller than the last example where there was a much larger variance because the points are further away from the central point. Does that help clear that up, Fatima? Okay, great. And does anyone else have any other questions? So the difference between variance and standard deviation, they're both giving you the same output, which is the variance, the spread of the data. So they're both getting at the same idea, but the difference is that variance is expressed in the units are the units squared. So if we're dealing with, let's say, weight, and we're looking at the weight of students in a class, let's say, if we're going to report what the variance is, it's going to be expressed in units of pounds squared, which doesn't really make too much sense to us because we don't use the unit pounds squared very often. So in order to fix that, to go back to our units, our regular units, we're going to take the square root of the variance. Once we take the square root of the variance, that is what's called the standard deviation, and that's expressed in the original units. So if we're dealing with pounds, your standard deviation is going to be expressed in units of pounds. It's not going to be expressed in units of pounds squared. So that's the reason why we use standard deviation, why it's reported more often than the variance. The variance isn't really talked about that much because its units are non-intuitive. So they're both getting at the same idea. They're both talking about your spread of your data, but the standard deviation's used more often because it's in the units of what you're dealing with. And so this is just to illustrate, the reason why we squared all the sum of the differences is because we want to get rid of those negative numbers. And then when we then calculate the standard deviation, we're taking the square root of that. So that's correcting for that squaring that we did earlier to get us back into the original units. Does that make sense? Yeah, so exactly. So the variance is not in units of what you're looking at. So we take the square root of it to convert to the standard deviation. Yeah, but they're both talking about the same concept. It's just that the variance is going to be the standard deviation squared. So it's typically going to be a larger number. But when you talk about, when you typically report the spread of the data, you're going to use the standard deviation because, if you talk about the mean and the standard deviation, they're going to be in the same units. If you're talking about the mean and the variance, those are going to be in two different units. So it's not as informative. No, they're not interchangeable. Those are two different concepts. So the standard deviation is describing the spread of your data, and the mean is describing the center of your data. So here the mean is in the center, 0, but we find that the variance here is 2, so your standard deviation would be the square root of 2. But what I was trying to get at is that the units of standard deviation and the mean are the same, but the units of the mean and the variance are different because the units of variance are going to be your units squared, and the mean is just going to be in your units. So that's why we use the mean and standard deviation to represent the center and spread of the data, respectively. Does that make sense? Okay, great. Any other questions? All right. If there's no other questions, well, I'll see you guys again next week, and good luck on the material this week. If you have any questions, feel free to reach out to us. And have a good night, everyone.